Hello, everybody. It's a pleasure to be once again back at Early Universe from Home. Today, I want to present some preliminary results on the dynamics of classical and quantum fields during inflation. The content of this talk is based on work in progress together with Guillermo Ballesteros and Gambin Egea in a project in which we try to address the following question. Under which conditions, if any, can a classical field, a stochastic classical field, be tuned such that its statistics mimics that of quantum fields during inflation? In order to address this question, I will begin by reviewing the standard picture of how we treat quantum fluctuations from inflation. I will then discuss precisely how we can mimic these quantum statistics using classical fields. I will then present two physically meaningful examples of this regarding the calculation of the bispectrum of a scalar field and the power spectrum of gravitational waves induced by scalars at second order. And finally, I will discuss some implications of our work for computational techniques in inflation. So just to set the stage, as it is well known, inflation is a phase of accelerated expansion in the early universe, postulated in order to address the shortcomings of the hot Big Bang paradigm, like the horizon puzzle, which in its simplest implementation relies solely on a single scalar field, slowly rolling down its potential, the so-called single field slow roll paradigm. The equation of the state of the field approaches that of dark energy, as its radiation energy density is dominated by the potential. And a crucial prediction of this inflationary paradigm is that the unavoidable quantum fluctuations of the field that is sustained in the accelerated expansion, when stretched into cosmological scales, give rise to the initial conditions for the cosmological inhomogeneities that we observe today. Importantly, some of the generic predictions of the inflationary paradigm regarding the nature and the characteristics of the perturbations it gives rise to are in remarkable agreement with the kind of initial conditions that we need to explain the spectrum of anisotropies of the cosmic microwave background. Moving into a more technical realm, the way we deal with quantum perturbations during inflation is the so-called ininformalism, in which we split the Hamiltonian of whatever set of fields we're interested in into a free part, which we know how to solve, and an interaction part, and then the time evolution of some operator, which is a functional of a series of fields appearing in the Hamiltonian, can be expanded into these terms which contain only free fields. And by this I mean that they are basically made up of the product of classical mode functions, so classical solutions to the equation of motion of the free Hamiltonian, times creation and annihilation operators whose commutation relations and statistics are well defined. In order precisely to retrieve some statistical information about these observables, we have to compute their vacuum expectation value, taking into account that the vacuum of the interacting theory, which is the one we're interested in, and the vacuum of the free theory, which is the one in which we know how to deal with creation and annihilation operators, are in principle not the same, and therefore we have to introduce this kind of I epsilon prescriptions, which basically match smoothly both vacuums in the asymptotic past. From a physical point of view, this is what the epsilon prescription does, and from a mathematical or computational point of view, what it does is basically a slight deformation of the integration contour that guarantees that these time intervals appearing here converge when the lower integration limit is pushed to minus infinity. All right, so far with introduction. Now moving into classical fields. So in order to explain classical fields, we will use the well-known rule of quantization by switching Poisson brackets in the classical formulation of field theory into commutators and including a factor of IH bar per each commutator. And in this way, we can write the dynamics of the classical field in a manner that is reminiscent and therefore easy to compare with that of quantum fields. In particular, the time evolution of the full classical field, so the one obeying the full interacting theory, can be expanded in terms of these pieces here, including only free classical fields, in terms of this formula, which is very much reminiscent of this formula by simply trading commutators by Poisson brackets according to this rule. And here, when I say free fields, what I mean is that these fields are basically made up of classical solutions, so these are just functions of time, classical solutions of the free Hamiltonian. And these quantities here that we call alpha, they are just numbers that encode basically the initial conditions of the field. Now, in order to mimic quantum fields with classical fields, we have to endow these classical fields with a stochastic nature, and therefore we will allow these numbers here to be complex valued random variables. Now, it's important to emphasize that these numbers, random variables, alpha, they are in principle unconstrained. They will not be fixed until we set a choice of initial conditions for the field. Unlike their quantum counterpart, the creation annihilation operators, whose statistical properties are completely fixed by the canonical quantization condition. So precisely the idea to try to mimic quantum fields with classical fields is exploiting the freedom in the choice of these initial conditions to choose the statistics of this alpha such that the statistics of the classical field matches that of the quantum field at a certain time, which we call T0, and then check whether this imposed agreement is preserved as we move forward in time or whether it is lost. So let's move into the first example that we are going to use to illustrate this kind of procedure. We are considering a scalar field, a self-interacting scalar field with a very simple cubic self-interaction. The power spectrum of this, the quantum tree-level power spectrum of this classical field, as it is well known, is basically just the square modulus of the corresponding mode function. And the quantum bispectrum, it can be computed basically by applying the inning techniques we mentioned before, and it can be shown to have this form here, where here you can see the I epsilon prescription appearing, and S and F are just basically related to the mode functions, so the solutions to the equations of motion of the free Hamiltonian for the field and the corresponding conjugate momentum. All right, so now we construct the classical field. So first of all, we have the free classical field, which, as we have explained, is the product of the mode function time these random variables to be determined. The full classical field in the interacting theory can be related to the free one through these nested integrals involving Poisson brackets that we described before. And what we do now is we compute the classical power spectrum and bispectrum of the interacting field using the expansion in terms of free fields and this equation for the free fields. And of course, okay, we obtain rather lengthy expressions, but the important thing is that these expressions are basically functions of the 2 and 3 point classical averages of all possible combinations of these quantities here, alpha and alpha conjugate. And now, by precisely imposing that the classical power spectrum computed in this way, which is a function of all these quantities, equals the quantum power spectrum at a certain time, tau naught, and same thing for the classical and the quantum bispectrum, we can basically read off what is the values of these 2 and 3 point functions that we need in order for these equations to hold, and we find them to be precisely the ones shown here. So now the classical field is fully characterized because these functions are basically solutions to the equations of motion of the free Hamiltonian, so we know those. These random variables are now fully specified in terms of the 2 and 3 point functions. This is the classical free field, and the classical field in interacting theory is related to the one in the free theory through these nested Poisson brackets. So we can now go ahead and use this information to compute the classical bispectrum at some later time, tau, subtract the quantum bispectrum at the same time, and see that indeed there is a non-zero difference between both of them. Now notice that this non-zero difference has exactly the form you would expect it to have, because it takes the form of an integral between tau naught and tau, meaning that if we evaluate this at tau naught, the result is 0, as it should be, because we are precisely imposing by construction that the statistics of the classical and the quantum field match at tau naught, And even imposing so, we see that the divergent classical and quantum evolutions make the statistics of the corresponding fields be different at a later time. Already by looking at this integral, we can recover a well-known result, because if we plug in here the functional form of the mode functions, one can see that this vanishes as long as the momenta here are sub-horizons. So basically that already at the matching time, they are sub-horizon. And this is related to the well-known fact that under certain conditions, but at least for a slow roll, if we introduce a phase of ultra slow roll, things can become a bit more complicated. But at least for slow roll inflation, when modes are sufficiently super horizon, they quantum fluctuations become classicalized. So in this sense, if we perform the quantum to classical matching sufficiently outside the horizon, then no extra difference between quantum and classical dynamics is generated, basically because the modes are frozen at this point. Okay, so we can actually solve this integral by plugging in here the mode functions and see what it looks like in more detail. Here we computed it in the late time limit to relate it to observations. The final result is a bit complicated, but we just want to point out a few details here. The first one is that, as one can see, the discrepancy between quantum and classical calculation grows with the matching conformal time. So conformal time grows in absolute value as we move backwards. This means that if we perform the quantum to classical matching deep in sub-horizon scales, we'll get a large difference between the quantum and classical results at late times. Also, we have checked explicitly that, well, of course, the quantum contribution, the quantum bispectrum, but also the classical bispectrum, and therefore the difference between both of them satisfies Maldacena's consistency relation for the power spectrum and the bispectrum, as it should, because this relation is not rooted in the classical or quantum nature of the fluctuations that appear in the problem. And of course, like the result we get here depends on tau naught, so on the matching scale. But one could be tempted to say, okay, why couldn't we apply some sort of I epsilon-like prescription to push this matching time backwards to minus infinity, but with some prescription that basically kills the tau naught dependence in a similar manner to what the I epsilon prescription does in the informalism. So if one does so, we would have just this term surviving here, a term which has poles at physical momenta, as it was already noted in this paper. However, using such a prescription to basically get rid by hand of the tau naught dependence is not consistent, as it is made manifest by the fact that this term alone, which would be the only term surviving in that case, does not satisfy the consistency relation for the power spectrum and the bispectrum that the whole difference between the quantum and the classical result does. So from here on, we will always keep explicit the matching time that we are using, both to keep our calculation natural and consistent, and also to make it simpler to discuss the implications for actual computational techniques in inflation, which I will discuss in a couple of minutes. Okay, so now moving to the second example we consider, which are gravitational waves induced at second order by scalars. I will go a bit faster here because although the calculations are a bit more complicated, the conceptual is exactly the same. So we have scalar perturbations, tensor perturbations. We rescale them to make the fields canonically normalized. We expand the quantum fields, the quantum free fields in terms of creation annihilation operators, which are independent for scalar and tensor perturbations, and also for the different polarizations of tensor perturbations. The three-level tensor and scalar power spectrum is once again a square modulus of the mode functions, which we denote with a tilde for tensor perturbations and no tilde for scalar perturbations. Going to second order in perturbation theory, things of course become more complicated. We get this kind of interaction Hamiltonians in which we have tensor perturbations coupled to a pair of scalars, and this gives rise to the so-called scalar-induced gravitational waves, which from the QFT point of view we can understand as loops of scalars that appear in diagrams in which we have two external tensor legs. So these two terms contribute to the one loop correction to the power spectrum of tensor perturbations. This one here through a quartic coupling scalar, scalar, tensor, tensor, and this one here through a pair of cubic couplings tensor, scalar, scalar, tensor, scalar, scalar. It might be complicated, but at the end of the day, we know how to compute the one loop correction due to each of these terms in the interaction Hamiltonian. Importantly, as the informalism promises to do, the result only depends on the classical mode functions that solve the free Hamiltonians, so the S and the S tilde. And we can play the same game as before, construct the corresponding classical fields for the scalar perturbation in terms of these random variables, construct the free classical tensor field in terms of this different set of complex valued random variables. We can use the nested formula with Poisson brackets that we saw before to relate this, so to expand the full classical field in terms of the free classical field. And once again, we go ahead and compute the power spectrum, in this case at one loop, in terms of these free classical fields. And again, what we get is a rather lengthy expression involving basically all possible combinations of 2-point functions and 3-point functions that arise in this combination. So this one with this one with this one, then the sum over polarizations of this one with this one, and so on. It's a rather cumbersome expression, but in the end of the day, the procedure is systematic. We take the result, we compare it with the 3-level tensor power spectrum plus one loop correction. We see what are the values that we have to give to each of these classical averages in order to have coincidental statistics at tau equal tau naught. We obtain these types of relations. And with that, we have the classical fields now fully characterized in terms of the statistics of these random variables. We go ahead, compute the one loop corrected classical power spectrum at some later time, subtract the quantum one loop power spectrum, and check that once again, indeed, there is a non-zero difference between both of them, which once again takes the form one should expect it to take with this kind of integrals ranging from tau naught to tau, basically because if we evaluate this difference at tau naught, by construction, it should vanish because it's precisely the point in which we are imposing the quantum and classical matching. And again, similar conclusions to the bispectrum case. If the matching is performed sufficiently on sufficiently superhorizon scales, the quantum versus classical difference will vanish, and the opposite occurs if we perform the matching on subhorizon scales. And with this, I reach my conclusions. So the basic conclusion that we have already emphasized a couple of times is that even if we tune a classical field such that it matches the statistics of a quantum field at a certain time during inflation, classical and quantum evolutions will diverge as time goes on, and the statistics of the classical and quantum fields will be in general different at later times, unless we are in the case in which quantum fluctuations have already classicalized on superhorizon scales. And as a technical remark, we said that the quantum to classical matching scale cannot be pushed back into the asymptotic past by performing anything analogous to an I epsilon prescription. Now, aside from these conclusions, I wanted to briefly mention a couple of implications of our conclusions for the computation of statistics of perturbations during inflation. So what our results, one of the things our results do is that they question the validity of computational approaches based on the classical evolution of randomly initialized scalar fields, as it is, for example, done in lattice simulations of inflation dynamics. So in this case, the field is set up on subhorizon scales, and then it is evolved by solving nonlinearly the classical equations of motion. As we have seen, this does not coincide with the quantum statistics at a later time. And also, the results we find highlight the importance of using proper QFT techniques to address the calculations of system of coupled tensor and scalar perturbations instead of classical calculations based on the Poisson brackets we used, or equivalently the more widespread Green's function. And I will finish here. Thank you very much for your attention, and looking forward to seeing you in the discussion session. Thank you very much.